So the topic is quantum harmonic oscillator, and what we have here is a relation which will be important to remember because we are not going to really derive everything here, but important relation, and based on that we are going to do some numericals. So that's important. So this topic may take around two classes, I guess, including today. Of course, we are going to do the tutorials also, but at the same time, then we are going to shift to the atomic physics part. So, when we are basically considering a quantum harmonic oscillator, first we should actually know what is the classical picture. That is very important. Classical. So, classically, when you basically, let's say, you have a box and you are attaching it to maybe a location which is fixed, right? And it will basically vibrate to and fro, and this will be actually called something which is actually oscillating, and the motion is nothing but simple harmonic motion. So that's the idea behind simple harmonic oscillator. Okay, this is simple harmonic motion, and if you're considering this part, and this is the object that is basically oscillating, so that is simple harmonic oscillator. Now classically it's different. You can see it with your naked eye and you can see that it's moving to and fro. Okay, but when we look into a quantum picture, we know that it is actually within a very small space. It is confined. For a quantum picture, we may say that we are basically having, let's say, an atom or a molecule, okay, or any particle which will actually go to this location and maybe come back. So it's basically, in a way, it's vibrating. Here also it's vibrating. Oscillation and vibration are more or less the same thing. Oscillation has got lesser frequency, vibration has got more frequency. So this is your simple harmonic motion. And classically, which we all have learned even in your class 11 and 12 also, we are actually representing it, and we say that the force on it is directly proportional to the displacement. Or we can just write it down as F is equal to minus kx. So this term minus kx is basically, or basically what we can say is, this law is actually nothing but the Hooke's law. Hooke's law. And what we can do from here is we can actually write down an equation. So for example, force we know is nothing but mass into acceleration, and kx we can take it on the other side, and we can simply write it down as kx is equal to 0. Now what is my mass is m. Acceleration, if I write it down in second order differential, it will be d2x dt square, that's your acceleration, plus kx is equal to 0. So this is your second order differential equation, and this will actually represent a simple harmonic oscillator, and this is more or less the classical picture or the idea that we have already developed. Okay, here we should know this derivation is also there, but we are not going to derive it. We know that k is equal to nothing but m omega square. Now this logic is also applicable here. K will remain as m omega square, or this term. Please make a note of this. This is very important. We may be using this relation again and again. Omega square. So it is just omega. Let's say it will be nothing but k root over of k divided by 2. We're going to use these results here. Okay. So this is more or less the classical picture that we have, which we have already learned in our lower classes. What we are going to do now is we are just going to look into the quantum mechanical picture. So as I said, we basically have an atom, or maybe an electron, or maybe any particle which is vibrating to and fro. As a result, it will be set in motion, and this will be having a quantum harmonic motion. It will be having a harmonic motion, quantum particle, so quantum harmonic oscillator. Okay. So similarly, we can actually use Hooke's law here. Forget about the sign. We can just write down F is equal to kx, where we know x is nothing but the displacement from the mean position. That's important. That's important. And just now we have seen that k is equal to m omega. So also derive it, but we are not going to do it. This is something which you should actually remember: m omega square x. Okay. Now, if you are basically considering quantum particle, and if you say it's a confined space, you should know what is the potential here. So v or u, right? We usually write it down as v or u. So what is the potential? I don't know that. But if I know the force, I can definitely find out what is the potential, because we know that force is equal to the change in potential with respect to position. This is the definition that we know. Again, we have learned it in our lower classes. So what we can do is we can simply say that the potential is equal to nothing but F dx. So that's important. So if I want to find out the total potential, I can just integrate this on both sides. So that means U would be nothing but, you know, this is the force and this is dx. So this is nothing but m omega square x. So I can take out m omega square, that's a constant, and integrate it. This is x dx. So that means this will be nothing but x dx is x square by 2. So it will be half m omega square x square. So if someone asks you to, what is the potential of a quantum harmonic oscillator, okay, what is the potential? So you can just simply write down this particular relation, and you will see there you're going to derive a lot of things based on this. For example, what is the probability of the existence of the particle? Okay, what is the probability of this? That also can be actually found out. There is a numerical problem in your tutorial also, which we are going to discuss. It is based on this particular formula. Now, as it's a quantum mechanical particle, we cannot use the classical picture, and we have to use the time independent Schrodinger equation. So, time independent Schrodinger equation. So, in order to solve this, we are going to use the time independent Schrodinger equation, which is something which you already know, which is nothing but minus of h plus square divided by 2n. Okay, this there are a lot of things that we need to do, a lot of numericals, math steps. So, we have to be very careful. Dx square plus V psi is equal to E psi. So this is our Schrodinger equation, which we already know, but we can definitely, modify this, and we can take E on the other side. There is a minus sign, so maybe I can multiply throughout by minus sign. Okay, this is minus, so I can take the minus on the other side. So I can have minus here. I'm just doing it so that we don't write too many steps here. So I can write it down as h cross square by 2m into d square psi. These steps are mechanical. We do it a lot of times. Plus, now there is a v minus sign. I've taken it on the other side. So if I've taken minus common, that means if I've taken minus common here, that means this will become minus. This will be minus. So it will be v minus v, and this is minus, it will go on the other side, it will become plus. So if I do the adjustments, it will be e minus v into psi is equal to 0. Remember, our v is this. Okay, we can definitely write that down at any point of time, but for now let's keep this doing. So we have this particular relation, and what we can do is we can modify it slightly more. We can divide throughout by this h cross square by 2m. This also, let's divide it by h cross square by 2m. This side it will be 0. So divide both sides by h cross square by 2m. So what happens is this term gets cancelled here. So we basically have it as d square psi dx square plus this will go up. So this would be 2m by h cut square. Okay, so that's there into e minus v into psi. So e is here minus v. We have just now calculated, so I can write it down as half m omega square x square into psi is equal to 0. So that's the first thing that we have to do. We have to write it down in terms of the quantum harmonic oscillator. So these are simple steps. You can easily remember this, and then we directly equate it with 0, and then we can actually think about it further, simplify it further. You can write it down as d square psi dx square plus 2me by h cross square minus half into m omega square x square x square. Okay, so this is e. There is a psi there. I missed out on the psi. So let's write down psi. This is psi is equal to 0. Of course, this time more here. So we have opened the bracket. So this is half m omega square x square into 2m by h cross square. So into 2m by h cross square into psi is equal to 0. So you might be thinking that why we are doing this. This is important because whichever sum you are going to do, whether be it a simple harmonic oscillator or maybe a quantum harmonic oscillator or maybe a potential well, potential box, everywhere we are more or less following the same step. Okay. So what we are going to do here is maybe we can take psi outside only. We don't need to take psi again and again. I will make it a bit simpler. I've just taken 2m by h cross square inside the bracket and I've kept psi here. So this 2 and this 2 will again get cancelled. Will become m square, okay, and so on. So what we do is now we replace the relations here: d square y dx square plus. Now what we can do is we can replace this. Okay, let me write it down here: 2me by h cross square. H cross square. Let's take this term to be alpha. Okay, and then we have got m omega. You see, this will become m square. This is omega square by h cross square. So let's take m omega by h cross. Let me take it as beta. So if I do that and try to replace it here, this equation will become simplified. This will become alpha minus. This will become beta square because it is m square omega square by h cross square. So this is beta. So beta square is square of that into x square into psi is equal to 0. So this looks simpler. We may be able to solve it, okay? But there are different techniques of solving such complex mathematical form because this is a second order differential equation. You have, a psi here. You have a psi here. Along with that, you also have an x. So we have to, do a lot of adjustments and use some techniques. So maybe we can take one of the first step. Maybe let's say let root over of beta into x is equal to q. Let's take another variable and let that variable be q. Okay. Let's see what happens now. We are not going to replace it here. What we are going to do now is we are going to find out d psi dx. Okay. And here we can do one trick here. We can write it down as d psi by dq into dq by dx. Now dq by dx means this term, this is q, and if you take ddx of this, you are just going to get root over of beta. Okay, so I'll just directly write it down as root over of beta, this term. This is nothing but root over of beta into d psi dx. Okay, what we can do now is we can again differentiate it, take the second order d square psi dx square. These are tricks to simplify this, and this would be nothing but d dx of root beta into d psi by dx. Okay, again more or less the same thing. We have d psi by dx as root beta. Okay, so I can take that root beta outside and then I can write it down as d dx. Sorry, this is d psi dq. Sorry. Yes. dq by dx, this is d psi by dq, right? So I'll write it down as dq. This is d dx, d psi by dq, d psi by dq. So now we know what is d psi by dq. We can actually keep it like that. We can write it like this. We can write down beta here. Sorry, beta here, and then this would be d dq. In place of x, I'm writing d dq. We will soon see why we're doing it. It will be nothing but d dq of d psi by dq, and I have written a dq. There was no dq, so I'll multiply it with dq, and I did not write down dx, so I'll write it down as dq divided by dx. And what's this term again? This term is again root over of beta. We know it. We've done it here. D psi by dq by dx, sorry, dq by dx is root over beta, so root over beta. So we can just replace it here, and what we are going to get is beta, because root beta into root beta is beta, and ddq of d psi by dq would be nothing but d square psi dq square. So this is something which we have. Now what we do is, this is important again in solving this. We're not going to do the entire detailed solution for this, but up to this point it's important. Let's see how much we can check with this. So that means, if I check this expression, if I check this expression, let's mark this as maybe A. Let's mark this as A. Now, if we compare it, we can actually do some replacements here. You can know d square psi dx square, d square psi dx square is this, right? So what I can do is I can write it down as beta. We are just changing the variables. In place of x, we are writing down everything in terms of q. D q square plus, we have got alpha minus, then we have got beta square, no issues, but it's x here. X is nothing but q divided by root beta, right? So x is equal to q by root over of beta. It is x square, so we'll square it out. So x square would be nothing but q square by beta square, so that's beta. So it will simply be written as q square divided by beta, and into psi, of course, is equal to 0. We're simplifying things here. Divided by beta on this side, divide this by beta, and of course divide this by beta. So that remains as 0. And if we simplify this, I'm going to get it to be d square psi dq square plus, divide this inside the bracket, it will be alpha by beta, so I'll take it to be alpha by beta, minus, you can see here, this beta and this beta will get cancelled. I'll be left out with only beta, divided by beta, beta gets cancelled, so it is just q square. Simple maths. So it will be q square. Let's put it inside the bracket, into psi is equal to 0. Somehow we managed to get only the variable here, and that's actually something which is helpful. And we are going to see, this simplification is important. Okay, this simplification is important. So if you look into q, this is root over of beta x, that means it is dependent on the displacement. If the displacement is large, that means this q square is going to be very large, and comparatively alpha is going to be small. Okay, alpha and beta both are going to be smaller quantities. So here we are going to do one assumption here that is important. Maybe I'll write it on here. For large q, if the q value is large, we know that this q square would be much greater than alpha divided by beta. We have to do these assumptions to look into the solution for this particular harmonic oscillator problem. So that means what we have here is, we can actually ignore this term, and we can write it down as d square psi dq square plus, we can ignore this because this is much larger, so I can simply write it down as this. Okay, so we have a minus here, so we take this minus of q square psi is equal to 0. This is the expression now which has got simplified when we use certain conditions and use some mathematical tools like substitution method and so on. Okay, now such solutions where we basically have a second order differential equation can be solved if we are basically having a form of psi. So there is a very simple mathematical technique where we basically take up a trial solution and test the equation which has been provided, the second order differential equation. So in this kind of problems, the trial solution, let's say for psi, is something which can be written as e to the power minus of q square divided by 2. You might think why there is not a plus and there is a minus. The reason is that q is something which we have already seen is dependent on x. So if it is plus, that means if this keeps on increasing, the displacement x will be more and more, and this result will be physically insignificant. You cannot have an wave function which is not confined. Whenever we are writing down a minus sign, we know this is more or less confined. Okay, even if the x value increases, this would be 1 divided by some term, so that psi value will actually be small. It's not going to be an infinite value. Okay, so this is a trial solution which we can use for psi. Okay, and whenever we are looking into a general solution, we need to have a coefficient before e, and this comes from mathematical physics. So I'll just write down this general solution. So the general solution for this is psi is equal to h, and h will be a function of q because the variable is q. We are saying here is q into e to the power minus of q square divided by 2. But we are doing quantum mechanics, and we don't have that much time for doing the mathematical part. This is actually a part of mathematical physics. Such equations are there in mathematical physics, and people usually solve them. And this coefficient, which we write it down as HQ, is actually called the harmonic polynomial. So this is going to be a function which is having a form, and the form is nothing but it's a harmonic polynomial. Now, if we want to find out what is this constant HQ, what is the form of this harmonic polynomial, it's going to be a humongous task. And I believe that even if this solution is asked in your exam, it cannot have so much marks. You can definitely start from whatever we have started with, and we're going to go up to this point. And if we actually solve the harmonic polynomial, okay, if we actually solve it, we can actually find out what is the energy. Okay, we can solve and actually simplify this, which is more important from the numerical point of view. We're basically going to have the energy E, which is equal to nothing but n plus half h cross omega. We are very much familiar with what is n. N is the principal quantum number, right? It talks about the energy state. And this particular expression tells me that the energy of the harmonic oscillator is also quantized. The energy of the harmonic oscillator is also quantized. So that's important. So we're talking about quantization. Now the question is, where does n starts from? And basically in this particular case starts from n is equal to 0, 1, 2, and so on. Right? So n is equal to 0 will actually represent the ground state. N is equal to 0 will actually represent the ground state. So what we can do is, for n is equal to 0, again very important, lot of numericals based on this. We can write it down as E0. For simplification, maybe we can write it down as E to the base n. Whatever is the energy at a particular energy level, E to the power 0 is equal to, n is 0, so I can simply write it down as half h cross h cross omega. So this is e to the power 0. Very important. You should also know the relation here, n plus half, and this is also important. Okay. Now this is at 0, so we basically call it as 0 point energy. So whatever is the energy at the ground state is actually called the 0 point energy. Something which we should actually remember is, whenever we are considering a quantum mechanical particle and we are saying it's a 0 point energy, it's just a term which says that it is at the ground state. But it does not say that the energy is zero. The energy is definitely not zero here, right? If there is a particle even at the ground state, it will have some kind of vibration, it will definitely have some frequency involved. So that means this omega cannot be zero. H cross is something which we know is not zero, 6.6 into 10 to the power minus 34 joule second. So if you do the calculation, you know what is the energy in the ground state. Okay. So what important point I'd like to tell you, one more thing here is, for example, let's say, I talk about, let me write down something like a note here. We talk about potential well, okay, potential well, which we have done before. potential well, one of the initial problems that we solved using Schrodinger equation. The energy which we saw was n square, h square, pi square divided by 2m square, where a is the width of the potential well, m is the mass of the particle, n is the energy state, which is the Planck constant. Okay. So here, when we talk about this, we say n is equal to 1, 2, and so on. It does not start from 0. The reason is, if I put n is equal to 0, this becomes 0, and we know that the energy is not 0 in the ground state, right? So that means whatever value we get, we write it down as E0. Doesn't mean that n is equal to 0. We can, let's say, let me not confuse you, let me write it down as 1. This is nothing but h square pi square divided by 2m a square. This is also the 0 point energy. Sometimes this is also referred to as the 0 point energy. So 0 point energy means whenever n is in the ground state. This is for the quantum harmonic oscillator, and this is for our potential well. So if you have a question, you have to just remember that what exactly they are asking. Are they asking for a potential well, or they are asking for a quantum harmonic oscillator? Okay. So let's continue this idea of quantum harmonic oscillator. As I said, we have to solve it, and after solving, we definitely get in one of the steps we get the value for energy, but we can also get the value for wave function, definitely, because if you think about a potential well problem, right? If we talk about the potential well problem in this note, we know what was our wave function, and our wave function was psi is equal to root over 2 pi L sine of n pi x divided by n. This was our wave function. Similarly, if we are basically considering this particular problem on the harmonic oscillator, this should also have a wave function. This energy is there, wave function is there, we found out in the process. Here we have just shown the energy, and we should also know the wave function. So as I said, wave function, we are not going to go into the detail. There are different ways of writing this wave function I've seen in different books, but you can remember any one that you want. You can also check your notes and what form they have written. We can also write it down in that way, no issues. Okay, but one of the more popular form is this. If we actually solve it, we're going to get it as m omega, and this is the sad part, is we have to remember this. Okay, we have to remember this because it's important. By pi h cross whole thing to the power 1 by 4. This is 1 by 4. Okay, so there are numericals based on this direct wave function application as well. 1 divided by root over 2 to the power n into n factorial. Okay, now this is actually a bit complicated. This is your harmonic polynomial h n x into, if we solve it and simplify it, we're going to get this e to the power minus beta x square divided by 2. So this is the wave function that is important. So this is important to remember. Important to remember. Quantum harmonic oscillator. Okay, some points that we should all know is important. Again, this is for solving numericals. First thing is 0 factorial is definitely 1, right? First thing that we should remember. Secondly is the harmonic polynomial. If I take this is the direct result which you can use. Don't think about solving it. You don't have time, and also you won't be asked, I guess. h0x. That means what is the harmonic polynomial when n is equal to 0? This result will also be equal to 1. So these two things you can remember. So if someone tells you find out the wave function at the ground state for a simple harmonic oscillator or quantum harmonic oscillator, you can simply write it down, this result. Okay, this would be there, this would be 1, and this would be this, right? So let me just write down on this ground state. Ground state of quantum harmonic oscillator. Very important. Very simple. It's psi 0x ground state is equal to, this will remain as m omega divided by pi h cross whole thing to the power 1 by 4 into 2 to the power 0 is 1, factorial 0 is 1, so this will become 1, h0x is again 1, so this will be just this term e to the power minus beta x square divided by 2. A simple issue, but then sometimes it becomes a bit complicated. We have to remember it in different ways. You can also find different forms for this. Okay, let me just tell you one form which is also there. I have seen some books they have written it that way also. So let me write it down as another form. Just change your variables. That's it. So that whichever text or anything you follow, you are not confused here. Psi naught x can also be written as alpha divided by pi. This is a simplified form which you can actually remember. More easy to remember this. Alpha by pi to the power 1 by 4 e to the power minus alpha x square by 2. Okay, alpha they use a number of times because I've seen, but you can write it down as beta by pi e to the power minus beta x square by 2. If you write down alpha here, you should write down alpha here. If you write down beta here, you should write down beta here. Okay, that's it. But I'm just writing down the different form. Don't get confused. The ground state, which one you should remember? I think you can remember this. This is more easy to remember. So this is remember this. Okay. And what is this alpha? Alpha is nothing but mk divided by h cross square whole thing to the power half. Okay. Again, we can write it down in different forms. We can write it down as root over of mk by cross, right, root t square, that's it, right, something which we already know. Also we have done before, should not forget this relation. What was our k, right, what is our k? So k is also important here. This is k here, so the k is okay. I think that should be what is k, this page. So classically when we check, k is equal to m omega square. Okay, so this is again important. So what we can do is this also, I'll write it down so that you remember everything at one go. K is equal to m omega square. So this form again can be simplified. If you put k is equal to m omega square, you can take it to be root over of m, and k is nothing but m omega square divided by h cross, which is equal to m square omega square, so that is nothing but m omega by h cross. So that can also be alpha. So alpha can be written in different forms. Okay, you have to be very careful. See, this is m omega by h cross. So m omega by h cross, I'm getting it here, m omega by h cross, and that is replaced, and that's why it is alpha. So don't get confused. Kind of important that we actually remember all these problems. Okay. Now, based on this, there are so many questions that have been given in the tutorial. But based on this, we can actually, solve some tutorial and numerical problems. Let's check one question here. Just put this here. So I'm not going to go serially here. We're just going to go topic wise. Okay. First one, I started solving, but there is some problem there. I just try to solve it clearly and then give it to you. But right now, let me just take this question. Okay. Mm, yeah, number 4. You can check number 4. This is directly related to the topic that we are doing right now. The question says that, okay, before that, is this whatever I have told, is it clear to you? Is it clear? Okay. Okay. So I will just tell you one thing that, once I teach you this, it's not that, you will remember. You have to do a bit of practice. That's very important. You have to remember those values and results. So probably I'll suggest that write down all the formulas that you have in quantum mechanics and put it in front of your study desk. Try to have a look at it every day morning, and then more or less you'll try to remember. Okay, it's important to remember these things. Okay, so let's just look into this. The potential energy of a harmonic oscillator is V is equal to half kx square. We already know it. Okay, we have seen potential energy is equal to half m omega square and so on. Okay, so that's not difficult. Okay, so let's take this question. Okay, let me see if my tools work here. Okay, so this is your potential energy. So let's take this question. Okay. So this is our question for now. Okay, let's check this. Just please say something. So this is our question. Let's try to understand this first. The question says that the potential energy of a harmonic oscillator is V is equal to half kx square. So what I'm being provided is this: V is equal to half kx square. That's my potential that is given. Show that the expectation value of V is E naught by 2 when the oscillator is in the n is equal to 0 state. So I am basically given n is equal to 0 state. That means we are talking about the ground state, and it's an harmonic oscillator, so n can be 0. If it was a potential well, n would have been 1 in the ground state, and we have to show that the expectation value of this is nothing but E naught divided. A bit of maths, a bit of complex maths. In fact, we are going to solve it. Okay, we are going to do it. So, in general, I told you that if you are actually going to find out the expectation value of any quantity, we already know it. We have to just integrate it from minus infinity to plus infinity. Consider the problem. So it's a simple harmonic oscillator. So we are going to take up the wave function for the simple harmonic oscillator. So I can take it as psi and x, and then I'm going to take the potential value here, whatever is being provided, and then I'm going to take the complex conjugate of this. Dx. So this is going to be my expectation value. Okay. Now the thing is, what should be the value of psi that we should include? That's again important. So we have already seen what was our psi. So we are going to maybe take a simplified form of this. So different forms are there. Let me take any form. Write down alpha form here. Psi n x we already know, and it's already said that that's zero. It's the ground state, right? So why to complicate things? Let's take it to be the ground state. So this is zero. This is also zero, and simply we can write down what is the ground state. So we have seen it. Okay, I kind of don't remember everything. This is by alpha by pi. Okay, so I can take this as alpha divided by pi to the power 1 by 4 into e to the power minus of alpha square divided by 2, right? E to the power, sorry, x and alpha x square. Sorry. Alpha x square. So it is alpha x square divided by 2. So now what I have is psi, and we have v. Now we have to integrate this. Okay, now we have to integrate this. Okay, so yesterday we were actually checking this, and we understood a bit about quantum harmonic oscillator, and I said that we need to remember these results. So the most important part would be this result, which is the energy quantized. And the second thing that we should remember is this particular relation, which is again in the ground state. If you go into any other state, the general form is this, which we have to remember. Okay, and based on that, we actually saw that there is a sum that we can actually solve, which is given in the tutorial. So what happened now is that we are going to look into the question once and just read through it, and then maybe we can try to solve it. Okay. So that's important. Did you try to solve this problem? Was it uh, done, or we can do it in detail today? This is important because if we do one or two sums like that, okay, we can solve other problems also which may be similar. There are certain results that we need to remember. Even if you're solved, I'd just like to discuss certain things which are actually important for this part. Okay. So, as I said, that the question is simple. We are being given potential energy of the harmonic oscillator in the form of half kx square, and we have to show that the expectation value is E naught by 2. So that means the first thing is we need to know the formula. Okay, so for knowing the formula, we can use this result. And since it's written n is equal to 0, that means we are considering the ground state. So that means that um, I can take it to be psi 0, and we have already seen that psi 0 is this, and this is our potential. And based on this, we can actually do our derivation. So this is actually a very, very descriptive question. We have to know all the steps, and I'm expecting that even if it is asked in your exams, they are going to give you good marks for this. This is again something which is there. So this is psi naught, and this is psi naught square. And as you can see that this is the complex conjugate, but we don't have any I term here. So that means this into this will be nothing but this square. So let's just try to square this term and find it first. Let's find out what is psi square x. So if I do that and I square this term, this would be nothing but root over of alpha by pi. If we square this, we get that 4 and 2 gets cancelled into e to the power minus 2 alpha x squared divided by 2. So these 2 and this 2 will get cancelled, and I'm going to get this term. So what we can do now is we can simplify things. We already know what is v, which is already provided. So it is minus infinity to plus infinity, and v is given to be half kx square kx square into this would be the square of that. So that is nothing but root over of alpha divided by pi into e to the power alpha x square. In exam or whenever you are practicing, I suggest that do everything in detail so that the things are clear and you don't miss out steps. If you miss out steps, there are chances that you will make mistakes. Let's take out the constants now. Half of k is a constant. I don't need it inside the integration. This is root over of alpha by pi. Again, it's a constant. I don't need it, so I will just take it out. Okay. So inside we are actually having a standard integral here. If we use gamma function and all, we have got an x square. We have got an x square minus infinity to plus infinity e to the power. Uh, I will start a minus here. Minus alpha x square dx. Okay. Now this result is actually something which is a standard integral. This result is actually a standard integral, and the result, I think we have discussed it once before, but then this is important, and let's try to remember this. Okay, let's try to remember this. I'll suggest minus infinity to plus infinity x square e to the power minus alpha x square dx is equal to pi to the power half root pi divided by 2a to the power 3 pi. So whichever we want to remember, you can take a title like this, or maybe I can write it down as half. This is pi, so I can write down as root pi. And this is a to the power 3 by 2, that means a to the power 1 plus half. That means I can write it down as a root a, whichever I may have write. So this is alpha, so let's not write down a, let's write down alpha. So it's alpha. Right. So this is the result, and we are going to put this result here. So let's do it. Half of k root over of alpha divided by pi into, again it's a half, and then this is root over of pi divided by alpha root alpha. So the aim to write down in this form is we can get cancelled. Uh, we can cancel out pi and alpha both sides. I've got 1/4 here. So the final answer that I have right now is 1 by 4 k divided by alpha. Okay. K divided by alpha. So we already have seen, we have an idea of what exactly is alpha. Okay, although we have not written it here, let's just go to the previous one. And we know that alpha is equal to nothing but mk by h plus square to the power half. We have tried simplifying this after putting the value of k is equal to m omega square, and alpha is nothing but m omega divided by h plus. So suppose in your exam they are not asking you this descriptive question and they're just giving you a problem which is this. Probably you need to remember what is the exact value of alpha. Okay. So what we can do now is we can do it. Okay. Let's try solving this. So this would be nothing but 1 by 4 into k. Let me take the original form of alpha, which was nothing but root over of mk by h cross. So I can simply write it down as 1/4 k h cross divided by root over of mk, which is equal to 1 by 4 h cross. Okay. Now you see this is h cross, this is k, this is m, this is k to the power 1, this is k to the power half, so it is 1 minus half, nothing but root k. Okay. So I can take root k on top, and at the bottom I've got root m. Okay. But we know that the k square or k is equal to m omega square, or omega is equal to root over of k by m. So I can replace this. So if I replace it, it will be 1 divided by 4 h cross omega. So when I simplify this, do my integration and put it, I get it to be 1/4 h cross omega. So if I do that, do I get my answer? Yes, we get it right. We already know that what is En. En is equal to n plus half h cross omega. And if you take the 0 point energy E naught, n is 0, so it is 0 plus half, so it is half h cross omega. Okay, so that means we can write down the expectation of value of V is equal to half into half h cross omega. And what is half h cross omega? E naught. So that will be nothing but E naught divided by 2. So that's proof. The good thing about doing these sums in detail is that you are getting a lot of sums which will be something similar. So you have to know the technique, that's important. So if you know once, then the other things can also be done. But you have to be a bit careful with you know energy term and momentum term and so on. So let me just talk about this next one, which is actually a bit more complicated. It's going to take. So is it clear? This one, is it clear to you? Okay. So let's go to the next one. I will share the recording at the same time. I'll also give you the PDF of this. I hope this gets printed and I can do it. Okay. Anyway, what's the next question? The next question is, what is the expectation value of the oscillator's kinetic energy in n is equal to 0 state? Now we are going to talk about kinetic energy. So it's not like V, because kinetic energy we know is nothing but we'll start from half mv square itself. Okay, and let's see what we can do in terms of kinetic energy. So let me take page. So here we are going to talk about kinetic energy. It's slightly tricky. We'll start with half mv square. Let it be anything. Obviously, this relation never gets old. It's important. I can write this as p square divided by 2m if I multiply and divide by m. So this would be p square divided by 2m. But in quantum mechanics, p is actually nothing but considered as an operator, and the function is something like this: E is equal to minus I h cross del x. So that means E is equal to minus I h cross by 2m whole square p square. Okay, sorry, mistake. Yeah, 2m is already there. So this is your 2m. In place of p, I have written minus I h cross, that's a square, and del x square, right? So it would be del square del x square. So if I do it, minus 1, this is minus square, so that's plus, I square is minus. So this would be minus of h cross square divided by 2m del square del x square. So this is my result. Okay, this is important. And when I do it, okay, I can actually get the answer. Just give me a moment. Hello. अच्छा आ रहा हूँ, एक सेकंड. So this is my E energy, and this is the result that I have to take into consideration. But there is a trick. The trick is this: there is a term which is del square del x square. So what we do now is let's just write down the form first, and then we can actually move ahead. So what we can say is, let's say I want to find out the average of kinetic energy. Let me write it down as T. E usually we use as total energy, so let me just take it as T, kinetic energy. And I can take it from minus infinity to plus infinity, but this time there is a problem. The problem is this: I will take this as psi 0 x, and then I will have the kinetic energy term, and kinetic energy term for us is nothing but minus of h cross square divided by 2m into del square del x square into psi naught x. The order is very important when we take out the expectation value. What happened in the previous case is we just have a term for the potential energy half kx square. There is no differentiation as such, so we have to do the simple combinations here. But there is a second order differentiation here when we are actually considering the kinetic energy term. So this will remain as psi naught x, but this part it will become psi double differentiation of that. Okay, so if we just simplify this, what we can do is we can take out the constant, so that is nothing but minus of h cross square divided by 2m, and this would be nothing but minus infinity to plus infinity, and this is the double differentiation of this. So first term would be nothing but psi naught x, but the second term won't be psi naught x, it will be in fact the double differentiation of that. So we have to simplify this. Since we have to double differentiate this, we are actually making it more complicated. So let's try to do it. Okay? So let's find out first what is del psi naught del x. So you have to do it step by step. Okay. So even if I don't number it, I hope you get the point here. Psi naught psi x dx is psi x of psi naught. So what's our psi naught again? We are going to take that result. Okay. So this psi naught will remain as this. Okay. So we have it here, right? Alpha by pi to the power 1 by 4 e to the power minus alpha x square divided by 2. So it would be alpha by pi to the power 1 by 4 e to the power minus alpha x square divided by 2. Okay, so that's our result. So we are going to differentiate this. So what we can do now is we can take alpha by pi. This is the thing that's going to take time in this particular sum, and then I have to tell del x of this. So this is minus alpha x square divided by 2. So we all know how to do it, right? So I will take, let's say, del y of this, where y is this. So this will be e to the power y into del y of this. So substitution method I'm using. I hope it's clear, simple. Alpha x square divided by. So it would be nothing but alpha divided by pi to the power 1 by 4 into, you can also try doing it, e to the power y into, this is my y term, so that's minus of alpha divided by 2, which can actually take it out. There is a minus sign. So minus plus, everything will matter at the end to get the final answer. Minus alpha into x square, so that is 2x. So let's cancel out this 2 and 2, and this is my result that I'm getting. So this finally would be nothing but alpha divided by pi to the power 1 by 4 into minus of alpha. I've taken the constant separate, and then these are the terms that I have. So it will be x e to the power y. Let it remain as y. Y is this. Let it remain as y because I'm going to differentiate it again. So after that we'll put the final result. Okay. So let's take out psi double dash. So this is your psi naught dash. So psi naught double dash is nothing but del x of del psi naught del x. So this would be nothing but del x of del psi naught del x is this term. So why to take the hassle of writing this again? I will just take the constants out first. So pi, sorry, alpha divided by pi whole thing to the power 1 by 4 into minus alpha, and then that would be del x of x e to the power y. So this would be, differentiation by breaking it into two functions. So it would be alpha by pi to the power 1 by 4 into minus alpha into e to the power y del x of x, right? So okay, let me just write it down. In fact, I can write it down as total derivative also, because we are talking only about the function of x here anyway. Into x into del x of e to the power y. So let me just write it down as del y of e to the power y into del y del x. And what is my y? Y is nothing but minus alpha x square divided by 2. So you have to be very careful. This is there. So we'll have the constant term here. This will become e to the power y plus this will be again e to the power y. So it will be x e to the power y into, this is minus alpha. So that's minus alpha into x square is 2x by 2. Same thing gets repeated. 2 gets cancelled, and what we can do now is we can actually kind of simplify this. So what we see here is that this term we can actually take it out. So I can simply write it down as alpha divided by pi to the power 1 by 4 into minus alpha. We have got e to the power y here, e to the power y here, so we can take out, it will be e to the power y, and within bracket it would be 1. Okay. And then we can take it as minus, and this is 1 e to the power y. This is x, and x will become x square, and alpha is there, so I can take it as minus alpha x square. So this is my term here. Okay. What you can do here is we can replace this y now. Originally we didn't have any y, so I will take it to be minus alpha x square by 2. So I'll write it down as minus alpha x square by 2. So this is my term for sine of double dash. So we have this now. We can actually replace it here in 1. So in 1, so we can say therefore 1 will imply that average of t is equal to minus of h cross square by m integration minus infinity to plus infinity. I have to first write down what was my psi naught. So psi naught was um, alpha divided by pi to the power 1 by 4. We have it that way, into e to the power minus alpha x square divided by 2. That was my psi naught, and then I have got this term. So this term again is nothing but alpha by pi 1 by 4 into, there is a minus alpha here, and then we have got this term here, e to the power minus alpha x square divided by 2 is a bracket 1 minus alpha x square dx. So this is my entire form of integration, and if you do it, we concentrate on this. So let's just take this part now. So it will be minus of h cross square by 2m, and then what happens is I've got this to the power 1 by 4 to the power 1 by 4, square it, so definitely you can take it outside the bracket. This would be alpha divided by pi into, this is minus alpha, let's take this out as well, minus of alpha. Can I take anything else out? No, everything else is a function of x, so we have to integrate this. So minus infinity to plus infinity, this and this we can multiply. 2 will be there, 2 will get cancelled, so I'll be getting it as e to the power minus alpha x square divided by 2 into 1 minus alpha x square dx. Okay. This entire term, let's take it as z now, so that we don't have to write this again and again. So let's say this is z constant, uh, integration minus infinity to plus infinity. This is this into this, so I will just take it to be e to the power minus alpha x square divided by 2 is not there, sorry, was just to multiply and to get cancelled out. So divided by 2 is not there. Alpha x square dx, just separating it out, minus integration minus infinity to plus infinity x square e to the power minus alpha x square dx. So again, mathematical physics helps us. These things are already solved using Gamma functions above, so we really don't need to concentrate on this. We have to just write down what is my result. Okay. So what I can do now is this: we can write down the final result and write it like this. Now this is again a standard result. Okay, minus infinity to plus infinity. Please remember this is the standard result when we are considering the limit to be minus infinity to plus infinity. This is nothing but root over of pi divided by whatever is the coefficient of x. So that's alpha. Okay, that's alpha. And for this also we have seen in the last one, what is this result? Root over of pi. You have to remember these results. Okay, important, divided by 2 alpha root alpha. So let's write down these results. This is root over of pi by alpha minus this result. This is again I can write it down as 1 by 2 times of alpha into root over of pi by alpha. So what we can do now is we can take out this pi by alpha outside. So let me just expand that again. Minus of h cross square by 2m root over of pi by alpha into minus of alpha, that's my z, into, I can take this root over of pi by alpha outside. Pi by alpha is the bracket, this is 1 minus 1 divided by 2 alpha. So we got this cancelled here. Okay, it can be the mistake. Alpha by pi, sorry. This is not pi by alpha, this is alpha by pi. This is alpha by pi. This is pi by alpha, so it will get out as cancelled. Okay. What we can do now is we can take this alpha inside. That's possible. Okay. So if we do that, now we can simply write it down as, okay. I think we did some mistake here. Let me just clarify this. Yeah, sorry. I think there is a problem somewhere. Some mistake is done. This is minus alpha. It's good. Okay, this is fine. Let's just check. I think we missed out one alpha somewhere. Okay, let me just check it once. Yeah. So when we actually took this term, we separated it out. This is e to the power minus alpha x square, fine. Minus x square e to the power minus alpha square is fine, but there is a minus alpha here. So we do have an alpha outside. This is something which we missed. So that means that this, if we take it, we will basically have a alpha here as well. We've taken the minus sign, fine. We have not taken this alpha. There will be this alpha. Okay. So what happens is with this result, this alpha and this alpha will get cancelled out. So it won't be 1 by 2 alpha. It will be just 1 divided by alpha and 1 divided by 2. That's it. So that means if you check here, this is nothing but 1 minus half, which is half. Okay. So what we can do now is we can just simplify this. This is 1 minus half, so that's half, and then there is a minus sign here. Okay, now it's fine. There is a minus sign here, there is a minus sign here, so this will become plus. So this would be h cross square divided by 2m into alpha into 1 minus half is half. So things have become much more simplified now. So this is 1 by 4 h cross square into alpha divided by m. So alpha, we know it is nothing but root over of mk by h cross. So 1/4 h cross square into root over of mk divided by h cross. That's my alpha into, there is an m here, we cannot mess up, 1 divided by m. So this and this will get cancelled. This will again become 1/4 h cross and this is nothing but m half and 1 minus, so this root over of k by m, right? K by m, and that is nothing but omega. So again this is 1/4 h cross omega. So this is, we don't need to repeat this, so I've already seen this is not divided. So that's our result. Okay, so what we see here is the conclusion is that if we take the expectation value of potential energy or the expectation value of kinetic energy, both are going to give me the result E naught divided by 2. And that is quite logical, because if you are considering any state and if it's a quantum mechanical particle, half of it may be potential, half of it might be kinetic. And if we add them up, we are going to get the total energy. E naught by 2 plus E naught by 2 is going to give me what is our result is E. Okay.